Parker's solar probe is the fastest thing we've ever built, yet it repeatedly swings past Venus to slow down. What kind of spaceflight trick is that? In late 2024, Parker dove to within about 6 million kilometers above the Sun's visible surface and hit roughly 190 kilometers per second. That's fast enough to cross the continental United States in half a minute. Yet, the mission plan includes a sequence of Venus flybys, close passes that look, on paper, like detours. And during those flybys, Parker doesn't fire its engines. No fuel burned, no thrust, just gravity. The tension is basic physics. Gravity is a conservative force, meaning it can store energy and give it back, but it shouldn't be able to permanently slow you down. So, how does Venus function as a brake pedal? Here's the first twist. If your goal is the Sun, you usually have to slow down first. Around the Sun, Earth moves sideways at about 30 kilometers per second. That sideways motion carries angular momentum, which is what keeps you in orbit instead of falling inward. If you simply point a spacecraft at the Sun from Earth, it still keeps almost all that sideways speed, so it doesn't drop straight down. It moves onto a slightly different ellipse and keeps missing the Sun. To truly fall deep, you must remove a huge chunk of that sideways motion, tens of kilometers per second. Rockets can't afford that. Parker launched hard, but the real strategy is to bleed off angular momentum a few kilometers per second at a time, using Venus as an intermediary. Step back. The braking we need is braking relative to the Sun, not relative to Earth. So, how can Venus take away speed without touching Parker? Now, switch viewpoints and ride along with Venus. This is a reference frame, a chosen moving viewpoint for measuring velocities. In the Venus frame, Parker approaches on a hyperbolic trajectory, an open swing-by path. Gravity pulls Parker in, it accelerates near closest approach, and then it climbs back out and slows again. Far away, the inbound and outbound speeds relative to Venus are the same, only the direction is different. If it came in at 7 kilometers per second relative to Venus, it leaves at 7 kilometers per second relative to Venus, just turned. That sounds almost boring, and that's the point. In Venus's own frame, the flyby is mainly a clean, lossless change of direction. Now, switch viewpoints back to the Sun, and the boring turn becomes a real speed change. Venus is orbiting the Sun at about 35 kilometers per second. Parker's heliocentric velocity is Venus's orbital motion plus Parker's motion relative to Venus. During the flyby, Venus rotates that relative to Venus velocity vector, so the way the two motions combine changes. Arrange the geometry so Parker leaves slightly against Venus's direction of travel, and a few kilometers per second gets subtracted from Parker's speed around the Sun. No engine could do that repeatedly without running out of propellant. Here's what happens next, physically. With less heliocentric speed at Venus's distance, Parker has less angular momentum. On the next orbit, it can't stay up as well, so its perihelion, the closest point to the Sun, moves inward. After several Venus flybys, that closest approach shrinks from a few dozen solar radii to under 10. Then, on each dive, the Sun's gravity does what gravity always does. It converts gravitational potential energy into kinetic energy, and Parker screams through perihelion at about 190 kilometers per second. Stepping back, Venus doesn't make Parker slow forever. It reshapes the orbit so the Sun can accelerate it later. But if Parker loses orbital energy around the Sun, where does that energy go? Into Venus's orbit, just imperceptibly. In the Sun frame, the spacecraft and planet exchange momentum through their mutual gravity, equal and opposite impulses over the course of the flyby. Take a 600-kilogram spacecraft and a 3 kilometer per second heliocentric speed change. That's about 2 million kilogram meters per second of momentum shifted. Spread that over Venus's 5 million billion kilograms, and Venus's speed changes by roughly 4 times 10 to the minus 19th meters per second. Real, but hopeless to measure. People compare gravity assists to an elastic collision with a moving truck, and that's useful in one specific way. The small object can gain or lose speed by trading momentum with a massive, moving object. Literally, though, nothing collides, and the spacecraft follows a curved path in Venus's gravitational field, and the planet follows an even tinier curved path in the spacecraft's field. Step back, the free energy is not free. It's borrowed from the planet's orbital motion. Venus slows Parker by taking a little of its orbital energy during each gravity assist flyby. The payoff is human scale. Those flybys let Parker touch the solar corona and improve our forecasts of space weather that threatens astronauts, satellites, and power grids. And the payoff is cosmic scale. The same momentum trading trick is how we can fling probes outward, inward, or even out of the solar system without carrying impossible amounts of fuel. Every gravity assist is a reminder that in space, speed is a relationship, not an absolute. Like if this was interesting, hit the subscribe for more and turn that notification bell on.